Welcome to Statics Day 2. If you were watching this, and you were in class today, I must apologize. For some reason, I did not record the lecture, so this may be a little bit different than what you saw in class, but essentially the same material will be covered here as was in class. Looking at the syllabus, uh, we finished up Chapter 1, which was the introduction to the course itself. We talked about gravity and a few other things. We'll kind of do a quick review of Chapter 1 in just a minute. Chapter 2, we're going to cover in 3 different sessions. It is essentially all of the vector math that you will need for the course for the rest of the semester. All right, let's take a look where we left off. All right, so we're starting chapter 2. Like I said, there'll be number of different sections. So this is today, and I actually did do part of section 2 today also. That recording is already on Canvas, but then next week we will finish this on Monday and this on Wednesday, those 2 on Wednesday. All right, just a quick review of Chapter 1. The main things to remember from Chapter 1 is that kilograms is mass, and we don't deal with mass, we deal with weight or forces. And this is typically what we say, forces. We don't deal in mass. So if a problem is given in mass, we know that we can put it into a force by using F equals ma, right? And the a that we will use for this class is the acceleration, which is 9.81 meters per second squared, or 32.2 feet per second squared. That's probably the most important thing to come out of this chapter, is all of that. And then also just basic unit conversion, but you should already have a good understanding of that part. All right, let's just do a quick trigonometry review. Let's say we have this triangle, and let's say we know side B and theta B, and we know side A, but we do not know theta A. How do we find it? If you remember, we used, if you remember back to trig, you used the law of sines. The law of sines is just a basic ratio. And the basic ratio states, and you can do this a number of different ways, either A over the sine of theta A, or you could write it as the sine of theta A over A is equal to B over sine theta B. Excuse me a second here. That's nice. And B sine theta B. Likewise, you can take that further and you can say C, oops, I got that wrong down the bottom, don't I? Sine theta C. I'm going to finish this one, should be sine theta C over C, and these of course are switched. So you can have it either way. It's just a ratio, and as long as you know 3 of them, you can find the 4th one. So in this case here, we don't know this theta A, and that's what we're going to solve for. So we can use these, and we can solve for it. Okay. The other important one is the law of cosines. The law of cosines states, all right, if I know, essentially if I know A, and theta C, I can solve for C. Okay, so and the way we do that, we would say C is equal to our two sides, a squared plus b squared minus 2ab cosine of theta c. Oops, that's a backwards c, isn't it? C square root. Okay, so that's how you would find the sine theta c. So those are the two main rules. The special case is when we have a 90-degree angle. We know, if we think of it, if I know the sine of theta c is equal to the opposite side, c over the hypotenuse, which can be rewritten also as the hypotenuse times the sine of theta c equals c. And likewise, we can do cosine theta c is equal to the adjacent side over the hypotenuse, or we can rewrite it as a cosine theta c equals a. These are the ones that you really need to know. We're going to use these a lot throughout the semester. In section 2.1, we're going to concentrate really on the law of sines and cosines, but then going forward, we will use this a lot, and you'll really, really need to use that. All right, just a quick going on as far as the basic concepts. We talked about last time scalar type things being just values themselves, some number, some size, such as mass, volume, length, are all examples of scalars. And then we talked about vectors, and vectors have both some magnitude and some direction to it. So weight or a force, so a weight is pushing us down to the center of the gravity, right center of Earth. Our force for weight is always down, straight down. Okay, and the way we'll designate it is, if it's a vector, we designate it typically in this class this way, with the letter of the vector and then the arrow above. The magnitude I will write this way, or sometimes the magnitude I actually just write as the letter itself. I don't use these other ones really. All right, so there's different ways that we can represent a vector. There's two main ways. The first one is polar coordinates. Right? Polar coordinates are essentially, we've given some length, right, and some direction. Right? So here is, this could be 5 kilometers out, and then we're at a rotation of 110 degrees. This obviously is not 110 degrees. But that gives us a specific location. It would be, out this way somewhere, right? So that is one way of representing a vector. Always a magnitude and direction. The other is we can do it in more of a Cartesian coordinate system. Here we're just saying B is, 3 kilometers east, and then 4 kilometers north. So this is our vector, our vector B. Let's write this again. B, 3 kilometers this way, and this is 3, and this is 4 kilometers this way. So this is this direction here, and this is, of course, 5 kilometers, because it's a 3, 4, 5 triangle. You can also do it in 3D. We could say east, north, and then up or something, or we can just give it in some X, Y, Z coordinate system. So this is our Cartesian way of representing it. So let's look at the components of a vector itself. A vector consists of a head, which is the arrowhead, and it consists of a tail, the starting point of the vector itself. It has a magnitude, so some length, and some line of action, right? Some direction. These are the components and nomenclature for a vector. Let's look at all the different basic vector algebraic things that we can do. The first thing is we can add vectors together. right? We can add a number of different vectors. So we have vector A and B, and there's two ways of doing it. Typically, we would kind of do it as head to tail. Uh, so, um, so here's our vector here, and we'll take this head and we'll put the tail of the next one there. And you see it doesn't matter the order, A, B, or B, A added first gives us this exact same vector, right? This is exactly the same result. And you can see that through this parallelogram addition, same thing. This, it would be like head to tail. Same thing. And depending on the problems, you'll look at it differently, each problem a little differently. We have the ability to do scalar multiplication. We take some scalar number, some value, and we can distribute that into each of the vectors. So this, if we did the vector addition first and then multiplied it, we could do that, or we could do the multiplication first and then add the vectors. We'll get the same result. This is a very useful way of using a scalar, negative scalar value, and we use it for subtraction of vectors. I can take this vector A, and if I multiply it by a -1, all it does is it turns the vector in the opposite direction and keeps the magnitude the same. So they're the same, but magnitude, but opposite direction. And the way it works in vector subtraction is I have these two vectors. You'll see this is the negative of that vector. Now I can add them together. Easy head to tail method. What if I have multiple vectors, right? I have vector A, B, and C. We said that it didn't matter the order for two vectors. Well, the same is true for three vectors, right? All of them could be added in any different way, and you'll see this vector R2 is the same for each case. Same direction, same magnitude, so it doesn't matter. And these are called vector polygons. Okay, so how do we actually add vectors together? Right. So one method is to use some graph paper and a protractor and a ruler, and a lot of patience, of course, and we can add these vectors together. You could also use CAD, right? You could use CAD and create those same vectors and then add them in CAD, and you'll get a more accurate one than just graph paper and a protractor and a ruler. Another method, the one we'll use for section 2.1, is we will use geometry and trigonometry. And the last method is if we can represent these vectors in a different way, we can use different techniques. And we'll find out that this is a lot easier to do, and we'll do this in section 2.2. But for now, I want you to concentrate on 2.1. Another term you'll hear is this resolution or resolve. We'll resolve these vectors into its components, right? So this is saying what vectors add up to f, right? So I could have a vector that goes here and a vector here. This could be vector A, this is vector B, right? Or I could have a vector that goes like this, vector A, or B. I could even say it's vector B, and I could say this one's vector A. Right? And if you think about it, we have infinite number of possibilities to equaling vector f. Conveniently, this is a nice setup right here. If we can do it as right triangles, right, it'll be a lot easier for us, as we'll find out later. But all those are possible solutions. So we can resolve our vector into different components, right? So one is, the top one is doing it in an orthogonal situation, essentially an x and a y coordinate system. That should be a y coordinate system. And that seems to be a very good way to do it. Again, this will be for section 2.2. We'll cover that later. For now, we're going to continue to do it in this non-orthogonal way. And in this case, we'll have to use, of course, the law of sines and the law of cosines, which we just discussed in the beginning of this lecture. So again, here are the law of sines and cosines. So how do we represent these vectors if we're given some situation like this? This shows two people and one is pushing horizontally on this crate with some force F, we would say, and this vector is being lifted up with 25 pounds at 25 degrees, right? And we want to kind of know our X and Y coordinate system for this also. So we could add these two vectors up, right? We could take these two vectors and add them up, whatever F is, and we would have some result in force R. I could replace these two vectors with, or these two forces, with this one and have the same effect on that crate. All right, with that said, let's take a look at this example. I'm going to cut the video right here and start a new one in just a second.